4 humans just flew behind the moon. No signal, no contact, no way to reach Earth. For 40 minutes, they were more alone than any person alive. And when they came back out the other side, they described a world that felt wrong. We will go to that far side together, to craters wide enough to swallow entire states, ancient surface cracks still splitting open today, rocks striking the moon in real time, and a solar eclipse no human had ever seen from that angle. If you enjoy this journey, subscribe. We are just getting started. Prepare yourselves. We begin. For all of human history, the moon has been hiding half of itself. Every poet who wrote about it, every scientist who mapped it, every child who stared up at it from a backyard, all of them saw the same face. Always the same craters in the same places. Always the same dark patches arranged in the same pattern. The moon rotates on its axis at exactly the speed it orbits Earth, which means one side is permanently locked facing us and the other side is permanently turned away. Scientists call this tidal locking. What it means in practice is that from the surface of this planet, you have never, in your entire life, seen half the moon. And here is where it gets strange. Several spacecraft have photographed the far side since the Soviet Luna 3 probe sent back the first blurry images in 1959. Orbiters have mapped it. Robots have studied it remotely. So you might reasonably assume that humans had at least seen it up close during the Apollo missions. But the Apollo trajectories were designed with precision landings in mind, and those paths did not take crews over the true far side. The Apollo 8 astronauts got the closest look, observing select features from orbit, but vast stretches of the far side remained beyond any human line of sight. That changed on April 6, 2026. On that day, 4 people flew their spacecraft, named Integrity, directly around the back of the moon. For 7 hours, they floated above terrain that no human eye had ever looked down on. They were not just breaking a record, they were seeing something for the first time in the history of our species. Astronaut Christina Koch described looking out the window and feeling something she could not immediately explain. The moon out there looked different. The darker patches, the ones your brain uses to recognize the moon's face from Earth, were in the wrong places. Her mind searched for a familiar pattern and found nothing. She later told reporters that something about what she saw signaled to her brain that this was not the moon she was used to seeing. That feeling was scientifically accurate. The far side of the moon is, in nearly every measurable way, a fundamentally different world from the near side. Its crust is thicker, its surface is more violently cratered. It has almost no volcanic plains. It carries geological scars that the near side simply does not. The moon we have stared at since the beginning of human civilization is, in a very real sense, the calm face of a much stranger object. And for the first 7 hours of April 6. But before we can understand what they found, we need to understand the machine that carried them there, and why this particular mission was unlike anything that came before it. The spacecraft that carried them had a name chosen by the crew themselves: Integrity. It was the right name, because what the Orion spacecraft actually represents, technically and historically, is a machine designed to keep 4 human beings alive in one of the most hostile environments ever attempted by our species. Deep space. Not low Earth orbit, where the International Space Station floats just a few hundred miles up, still partially shielded by Earth's magnetic field. Deep space, where the radiation environment is different, where rescue is impossible, and where any system failure becomes a conversation about survival. Orion is 30 feet tall and built to withstand re-entry speeds of around 25,000 miles per hour. The heat shield on its bottom is the largest ever flown. It had to be, because returning from lunar distances means hitting the atmosphere much faster than a spacecraft coming down from low orbit. The thermal energy generated during that descent is roughly 8 times hotter than the surface of the planet Mars. The shield absorbs it so the crew does not. Inside, 4 people lived for 10 days in a volume roughly comparable to a large walk-in closet. Commander Reed Wiseman, pilot Victor Glover, and mission specialists Christina Koch and Jeremy Hansen ate, slept, and conducted scientific observations in that tight space, while traveling a distance no human had covered since 1970. Here is something that surprised even the crew. Christina Koch later described getting a chance to manually pilot the spacecraft and being struck by how responsive it was. The team intentionally shut down some thrusters to simulate an engine failure scenario, and she flew it by hand. She called it amazing, a deep space spacecraft, flying by hand. But integrity was also a test. Every system, every procedure, every unexpected moment on this mission feeds directly into the design of future missions that will actually land people on the moon. Artemis 2 was the last crewed test before boots touched lunar soil. And during that test, the spacecraft had to do something that no crewed vehicle had done in over 50 years. It had to go behind the moon. The moment that happened, something remarkable occurred. Not a malfunction. Something far more human and far more unsettling than a malfunction. All contact with Earth stopped completely. The silence began at exactly the right moment and lasted exactly as long as planned. When integrity passed behind the moon, the lunar mass itself blocked every radio signal between the spacecraft and every antenna on Earth. Mission control in Houston went quiet. The screens that track spacecraft telemetry went flat. For 40 minutes, no one on Earth knew what was happening, 250,000 miles away. This was not an emergency. Engineers planned for it, prepared for it, built the mission schedule around it. But knowing something will happen and experiencing it are two entirely different things. Flight controllers who had spent years training for this mission sat at their consoles and waited. There was nothing else to do. Inside Integrity, the crew was busy. Commander Reed Wiseman later described the experience of being on the far side during the blackout. Victor Glover, when asked what it was like to be completely cut off from the rest of humanity, said something that landed hard. He said it was actually quite nice. The crew was focused on their work, moving through their observation checklists, photographing the surface below them, calling out geological features to each other. In a strange way, the absence of radio contact created a kind of focused calm. Think about what that silence actually means. Every other human being who has ever lived was on one side of that moon. Every city, every ocean, every person you have ever known. And 4 people were on the other side, with 250 miles of solid rock between them and the rest of our species. The last time humans experienced that kind of isolation was during the Apollo missions, when command module pilots orbited the moon alone, while their crewmates descended to the surface. Astronaut Al Worden, who flew Apollo 15, once described those solo orbits as the most alone any human being had ever been. The Artemis 2 crew shared that specific category of aloneness. 4 people together, completely unreachable. When the signal came back, it was brief and crisp. Integrity re-emerged from behind the moon, and Houston heard the crew's voices again. But the 40 minutes before that moment had already changed something, because what the crew had been looking at during that blackout was the far side, up close, with their own eyes. And it did not look the way they expected. Something about the surface felt off. Christina Koch had already said as much. But the deeper reason for that feeling goes back billions of years, to a mystery that scientists have been arguing about since the first spacecraft photograph of the far side shocked the entire scientific community in 1959. Christina Koch described looking out the window and feeling her brain search for something familiar. She and her crewmates had spent months studying lunar maps, memorizing crater shapes, training in geologically similar environments in Iceland. They knew what the far side was supposed to look like on paper, but paper and presence are different things. When she looked out the window and scanned the surface below, she said the darker regions were simply not in the right places. Her description was precise. Something about what she was seeing signaled that this was not the moon she was used to. That reaction was physiological before it was scientific. Human brains are wired to recognize patterns. We have spent hundreds of thousands of years looking at the same face of the moon. The near side has become something close to an instinct. Its arrangement of dark plains and bright highlands is as recognizable to us as a face we have known all our lives. The far side breaks that pattern entirely. On the near side, roughly 31% of the surface is covered by vast, dark plains of solidified volcanic rock. These are called maria, which is Latin for seas, because early astronomers thought they were bodies of water, They are wide, flat, and relatively smooth. They give the near side the pattern that generations of humans have called the man in the moon. The far side has almost none of that. Scientists estimate that only around 1% of the far side surface is covered by volcanic plains. Instead, there are craters, thousands of them, packed together so densely in some regions that new craters sit on top of older ones. The terrain is rougher, more extreme in elevation change, and almost entirely lacking the smooth, flat basins that make the near side look the way it does. So when Coke looked down, her brain found none of the familiar landmarks. The dark patches were wrong. The proportions were wrong. The textures were wrong. The moon outside the window was, geologically speaking, a completely different place. And there is a reason for that. A reason that is one of the most debated and frankly astonishing unsolved problems in planetary science. The moon has two faces that formed differently, evolved differently, and look so different that scientists have spent decades building competing theories to explain why. What the Artemis 2 crew saw was the physical proof of that mystery, up close, for the first time. And the deeper you go into the science, the stranger it gets. The moon has two faces, and they should not be this different. When scientists first measured the moon's crust, using the Gravity Recovery and Interior Laboratory mission in 2012, they found something striking. The crust on the far side is roughly 37 miles thick. On the near side, it is around 25 miles thick. That is a difference of about 12 miles of solid rock, and it matters enormously for understanding how the moon evolved. Thickness of crust controls everything that happens below it. When a large space rock crashes into a world with a thin crust, it punches through to the molten rock below. That molten rock, called magma, wells up and floods the crater, spreading outward and cooling into the flat, dark plains we call Maria. That is exactly what happened on the near side billions of years ago. Enormous impacts punched through the thin crust, magma flooded out, and over millions of years those floods solidified into the dark plains that make up the pattern humans have recognized since before recorded history. On the far side, the crust was too thick. Space rocks hit just as hard. Some craters there are even larger than the ones on the near side, but the crust did not yield. The magma below could not break through. So the craters stayed as craters, dry and sharp and ancient, accumulating on top of each other across billions of years without ever being smoothed over by volcanic flooding. The result is the rugged, heavily cratered landscape the Artemis 2 crew looked down on, a surface frozen in the record of every impact it ever received, because nothing ever came up from below to erase it. And now the question gets harder. Why is the far side crust thicker in the first place? If the moon formed from a single giant impact event, when a Mars-sized object struck early Earth, the material that coalesced into the moon should have distributed somewhat evenly. The two hemispheres should be broadly similar. They are not, and explaining that gap has produced some of the most creative and contested science in modern planetary geology. What happened to make one side of the moon so fundamentally different from the other is a question that goes back to the very first hours of the solar system. And the answer, if scientists are right, involves something that happened to the moon when it was still a glowing ball of liquid rock, barely cooled from its own birth. 4 billion years ago, the moon was not a grey, cratered world. It was a sphere of molten rock, glowing hot from the energy of its own formation, slowly cooling from the outside in. As it cooled, minerals began to crystallize. The lightest of those minerals, a pale material called plagioclase feldspar, floated upward through the liquid rock the way oil rises through water. It gathered at the surface and formed the early crust. Here is where the asymmetry begins. Scientists now believe that during this cooling phase, one side of the moon faced a very hot young Earth, while the other side faced the cold of open space. The near side, baking under the heat radiating from a newly formed planet, stayed hotter longer. The far side, exposed to deep space, cooled faster. And because plagioclase crystallizes more efficiently at lower temperatures, more of it formed on the far side and more of it piled up there. The result was a thicker crust on the far side before the moon had even finished forming. The die was cast in those first few million years, while the rock was still liquid. This theory, developed by a researcher named Wen Shuai Liu, is currently regarded as a leading explanation, but it is still classified as a hypothesis, one that scientists plan to test with computer simulations of the early lunar cooling process. It is elegant, it is supported by geochemical data, and if it is correct, it means that the Earth itself shaped the moon's two faces simply by being hot. But there is a competing explanation that is even stranger. Some scientists argue that a giant impact after the moon had already formed a solid crust, created a massive wave of heat that traveled through the lunar interior and concentrated certain elements on the near side. The South Pole Aitken Basin, the enormous crater at the moon's south pole, may be the scar left by that second catastrophic collision. The heat plume from that impact, according to researchers at Brown University, would have carried rare heat-producing elements toward the near side, making that hemisphere warmer and thinner, while the far side stayed cold and thick. And then there is a third idea, which is possibly the most extreme of all. Scientists have proposed that the moon was not always alone. There may have once been two moons in the sky. This idea, developed by planetary scientists studying why the far side crust is so much thicker, proposes that shortly after the moon formed, a second, smaller companion moon formed alongside it, both of them created from the debris of the same original giant impact that made our moon. For tens of millions of years, both moons orbited Earth together. Then, gradually, their orbits shifted until they collided. The collision would have been slow by cosmic standards, more of a slow merger than a violent smash. The smaller companion, perhaps a few hundred miles across, would have pressed into the far side of the larger moon and added its material to the surface there. That extra layer of crustal material would explain why the far side highlands are so much thicker and why they sit at higher elevations than the near side. This theory is classified as a scientific hypothesis, supported by calculations but not yet confirmed. It requires the right orbital conditions and the right timing. But the math works out. Two moons, born from the same debris cloud, orbiting together for millions of years, eventually merging into one. If this happened, then the face you see when you look up at the moon tonight is a mosaic of two separate objects. The near side formed one way, the far side built up from the remains of something else entirely. And there is something in the geology that hints at this. The far side highlands are not just thicker, they are compositionally different in ways that suggest a different cooling history, a separate material accumulation. The Artemis II crew flew directly over those highlands. They photographed the ancient terrain and described it to mission scientists in Houston. The images they sent back show a surface layered with impacts that reach back to the earliest period of the solar system, when the collision rate was so high that worlds were being reshaped every few million years. One of those ancient impacts left behind a crater so enormous that it challenges the imagination. The Artemis II crew had it on their observation list, and when they finally saw it with their eyes rather than through a spacecraft camera, the scientists in Houston fell momentarily quiet. Roughly 3.8 billion years ago, something large hit the moon. The object was almost certainly an asteroid, large enough and fast enough to unleash an amount of energy that is genuinely difficult to put into words. The impact punched a hole into the lunar surface and sent shockwaves rippling outward in concentric rings, like the pattern you see when a stone hits still water. Except that each ring in this case was a mountain range, carved into rock, hundreds of miles long. The result is called the Orientale Basin. It measures nearly 600 miles across. To put that in perspective, the state of Texas is about 800 miles wide at its widest point. The Orientale Basin would swallow the entire state of California and still have room left over. Because it straddles the boundary between the near and far sides, portions of it are theoretically visible from Earth, but only barely, only at certain angles, and never in full. The Artemis II crew saw the entire basin from their orbital vantage point, and they saw something that even high-resolution spacecraft images had not fully captured. The texture, the terraced walls, the central floor, the way the blast rings grade from sharp relief near the center into lower, rounder ridges farther out. Scientists study Orientale because it is remarkably well preserved. After 3.8 billion years, the basic structure of the impact is still legible in the rock. The reason is that relatively few subsequent impacts have disturbed the area. It sits as a record of what a major impact event looks like, frozen in time. During the flyby, the crew focused on Orientale as one of their primary geological targets. They described its features aloud to mission scientists, calling out color differences and texture variations that help researchers understand the composition of the rock layers exposed by the impact. Those layers matter enormously. They are a cross-section of the moon's early history. Rock pulled up from deep inside the moon by the force of the collision, rock that sat below the surface for billions of years and would never have been accessible any other way. But Orientale was not the only target. To the northwest sat a different kind of crater, one that tells a completely different story, one where the details have been erased. The Hertzsprung Basin is what happens when time wins. It sits northwest of Orientale on the moon's far side, and it is nearly 400 miles wide. When it formed, it would have looked broadly similar to Orientale. Sharp rings, defined walls, a clear central structure. But Hertzsprung is older. Far more impact events have happened on top of it, beside it, and inside it across the billions of years since it formed. The original features have been worn down, softened, and partly buried by the relentless bombardment that the far side of the moon receives. The Artemis II crew observed both basins during their flyby, and that pairing was scientifically intentional. By comparing a well-preserved basin like Orientale to a heavily degraded one like Hertzsprung, scientists gain a time-lapse of lunar geology. They can see what a basin looks like fresh, and then see what that same type of structure looks like after billions of years of additional bombardment. What they found in that comparison is useful for something far larger than moon science. The far side's cratered surface is, in a very real sense, a record of the bombardment rate in the inner solar system across 4 billion years. Every impact on that surface is a data point. The density of those craters, their sizes, their layering on top of each other. All of it tells scientists how frequently large objects were flying through this part of space at different points in history. And if the moon was getting hit at a certain rate, Earth was getting hit too. Probably more, because Earth is bigger and has stronger gravity. The difference is that Earth's surface is constantly renewed by plate tectonics, erosion, and volcanic activity. The record is wiped clean over millions of years. The moon has no plate tectonics. It has no weather. The craters stay. Every impact the far side ever received is still there, stacked up, overlapping, creating a geological archive that Earth simply cannot provide. The Artemis II crew flew over that archive. They photographed it, but they also witnessed something live, happening in real time, that made the ancient impact record suddenly feel immediate. While the eclipse darkened the lunar surface, the crew saw flashes of light. 6 of them, brief, sharp, unmistakably real. Each one was a meteoroid, a space rock traveling at many thousands of miles per hour, striking the moon's surface and releasing enough energy on impact to produce a visible flash of light from 4,000 miles away. Astronauts during the Apollo missions had reported seeing such flashes, at least 3 confirmed during those flights in the 1960s and 70s. Scientists knew the moon was being struck regularly, but seeing it happen, 6 separate impacts observed in real time during a single hour-long observation window, made the abstract suddenly concrete. The moon has no atmosphere. On Earth, even a small rock burns up as a meteor when it hits the upper atmosphere. That streak of light you call a shooting star. The moon has no such protection. Every object that enters its vicinity hits the surface directly. The rocks do not slow down. They do not heat up and disintegrate harmlessly overhead. They arrive at full speed and release all of their energy directly into the crust. The current estimated impact rate across the whole lunar surface is many thousands of impacts per year, ranging from tiny dust grains to boulder-sized rocks. The 6 flashes the crew witnessed were on the near side of the moon, near and south of the equator, which meant there was a scientific bonus. Amateur astronomers on Earth who monitor the moon for impact events might have seen the same flashes from their backyard telescopes on the same night. Now tie that back to Earth. We sit inside the same debris field as the moon. The same rocks that strike the moon are also crossing our orbit. We are shielded by our atmosphere and lucky that the largest ones are rare. But 4 billion years ago, before the debris field had cleared out, the impact rate was orders of magnitude higher. The Far Side crater record is not just a moon story. It is the story of how violent the early solar system was, and how narrowly habitable conditions on Earth survived that violence. And what the Far Side geology confirms is that the moon took the hits so Earth did not have to. At the closest point of the flyby, integrity was just 4,067 miles above the lunar surface. That sounds like a large distance until you put it next to something familiar. The distance across the continental United States, from Los Angeles to New York, is about 2,800 miles. The crew was roughly 1.5 continental United States above a surface that no human had ever looked down on in this way. From that altitude, details were visible that no spacecraft camera had ever captured with human context. Color differences in the rock, textural variations between crater floors and surrounding highlands, the way certain areas caught light differently, hinting at differences in mineral composition. The crew called out what they saw to mission scientists in Houston, describing features in real time, drawing on their geological training from Iceland and other Earth-based analog sites. They documented ancient lava flows confirmed on the far side in regions where models had predicted the crust would be too thick to allow volcanic eruption. Those flows are smaller and less dramatic than the vast Maria on the near side, but their existence raises questions about the internal heat history of the moon. If lava reached the surface in those regions despite the thick crust, something drove it there. Scientists are now analyzing the images the crew captured to understand what. They also documented surface fractures, long, shallow cracks running across the terrain where the rock has been split, likely by the cooling and contraction of the moon's interior over billions of years. The moon is not geologically dead. It has continued to shrink slightly as its interior cools, and those fractures are the surface expression of that process. Technically, moonquakes are still detected by seismic sensors placed during the Apollo missions. The moon is alive in a way that does not show up on any postcard. The crew was looking at all of this with their own eyes, narrating in real time, doing something that no robotic mission could replicate, applying human pattern recognition and intuition to a landscape that had never before been observed by a person. And then the crew turned their attention to something they had not been looking at, something that had always been behind them as they observed the surface below. They turned and looked at where Earth should have been, and it was gone. Jeremy Hansen was the first Canadian to travel beyond low Earth orbit. He floated at the window of integrity and watched Earth sink below the edge of the moon. He described the experience as emotional, full of joy, full of a sense of disbelief that was hard to shake even in the middle of all the work. He said that right away. From the moment they had left Earth's vicinity, he felt humbled. He described watching 4 people get to be out there together as something that brought him to his knees. But when Earth set behind the moon, it was something specific. Every human communication system, every GPS satellite, every internet connection, every radio signal in the history of civilization was on the other side of that grey horizon. The crew was not just physically far from home. They were behind an object large enough to block every wavelength of signal that humanity produces. They were, for those 40 minutes, genuinely unreachable. There is a concept that astronauts describe called the overview effect. It typically happens when a person sees Earth from space for the first time and experiences a profound shift in perspective, an emotional recognition that the planet is a single, fragile, finite object floating in a void. Most astronauts who describe the overview effect talk about seeing Earth from a few hundred miles up, still close enough that continents are visible, still close enough that the atmosphere is a vivid blue band at the edge. Hansen and his crew experienced a different version. They watched Earth not just shrink, but disappear entirely. One moment it was there, a crescent barely fitting over the lunar limb, partly in daylight showing Australia and the Pacific Ocean, partly in night. Then it was simply gone. Behind the rock, unreachable. Scientists have a word for that visual moment, Earthset, and the photographs the crew captured of it are among the most striking ever taken. Earth at the edge of the moon, then gone. But something else was happening at the same moment. As Earth vanished, the geometry of the spacecraft, the moon, and the light of the star we orbit was aligning into something no human had ever experienced from that specific position in space. Before we get to the eclipse, there is a moment that deserves its own chapter. At roughly 2 in the afternoon Houston time, while the crew was conducting observations of the far side and calling out features to mission scientists below, Commander Reed Wiseman spotted 2 small, unnamed craters in the pockmarked terrain. He proposed names for them. The first he suggested calling Integrity after the spacecraft carrying them. A fitting name. A crater on the moon named for the machine that brought humans close enough to see it. The second crater, sitting just northeast of the first, on the boundary between the near and far sides, he suggested naming Carol Taylor Wiseman, was Reed Wiseman's wife. She died on May 17, 2020. She never got to see her husband fly to the moon. She never got to hear the word integrity echo back from mission control, or watch the images of Earthsat appear on screens around the world. But now, if the International Astronomical Union approves the proposal, her name will be on the surface of another world forever. The naming of craters follows formal rules. The crew's suggestions are provisional until reviewed and accepted by the governing body that controls all celestial nomenclature. But the submission will be made, and the moment Wiseman spoke the name Carol aloud from behind the moon, something shifted in the emotional register of the entire mission. Science and grief and wonder do not usually share the same sentence, but they did in that moment. A man who had just broken the record for the farthest any human had traveled from Earth chose to use that position to remember someone he had lost. He placed a name on a world that no human had looked at with their own eyes until that day. Mission control went quiet for a moment. Then they confirmed the transmission. Then the crew went back to work. And what came after that is one of the most visually overwhelming things any human being has ever described from space. The photograph exists. You can look at it. A grey, cratered lunar surface fills the frame in the foreground. The rock is ancient and textured, lit by angled light that throws the crater rims into sharp relief. At the upper edge of the frame, at the very limb of the moon, is Earth. Small, a crescent, partly in daylight, showing swirling clouds over Australia and the Pacific, partly in the dark of night. And in the photograph, it is clearly about to slip below the edge. 3 minutes after that photograph was taken, Earth was gone. Earthsat is not a new concept. The Apollo 8 crew took what became one of the most famous photographs in human history, Earthrise, our planet climbing above the lunar horizon. That image, taken in December 1968, is credited with fundamentally changing how humans thought about their own planet. Seeing Earth as a small, fragile sphere against the darkness of space altered the environmental consciousness of an entire generation. The Artemis 2 crew captured Earthsat. The same idea in reverse. Not Earth rising into view, but Earth dropping away. And this version had something Apollo 8's did not. The crew capturing it were on their way behind the moon. They knew that in minutes, that crescent would vanish entirely. They were not passing by on an orbital path that would bring Earth back into view in minutes. They were going around the back, into the blackout, into the silence. The disappearance of Earth was not just a visual event. It was the end of contact. Astronaut Hansen later said the photographs the crew sent back were spectacular, but pale compared to the real thing outside the window. He was watching Earth disappear with his bare eyes. No camera captures exactly what that looks like. The scale, the darkness around it, the sudden absence when it is gone, and then the moon itself stepped between them and the star we call home, and a different kind of light appeared. Just after Integrity came back around from the far side and resumed contact with Earth, the geometry of the mission produced something that scientists have been anticipating for months. The moon passed between the Orion spacecraft and the light of our star. From the crew's position, the moon was not a disk in the sky. It was a vast wall of grey rock filling most of their view, and behind that wall, the light of our star disappeared behind the lunar edge, leaving only a glowing ring. From Earth, a total solar eclipse is a rare and stunning event. The moon and our star appear almost exactly the same size in our sky, purely by geometric coincidence. And during a total eclipse, the moon covers the disk almost perfectly, revealing the corona around the edges. From the Orion spacecraft, it was different. The moon appeared much larger than the star from that close vantage point. The star's disk did not just disappear behind the moon's edge, it was swallowed. And the eclipse lasted not the few minutes of totality that eclipse chasers on Earth chase across continents. It lasted nearly an hour. Commander Wiseman described it as an absolutely spectacular, magnificent experience. The crew used special eclipse glasses, the same type distributed for the 2024 total solar eclipse that crossed the continental United States, to protect their eyes during portions of the event. They photographed it continuously. The images they sent back show the darkened moon from the front, with the solar corona glowing around its entire circumference. And around the edges of the moon in those photographs, distinct points of light are visible: Saturn, Mars, Venus, the planets of our solar system, usually hidden by the glare of our star, appearing all at once in the sudden darkness. But the corona was the centerpiece, and what the crew saw inside it was something that scientists had specifically hoped for, something that the crew described with a specific and unexpected comparison. The corona is the outermost layer of our star's atmosphere, and it is one of the great unsolved problems in astrophysics. The surface of our star is roughly 10,000 degrees Fahrenheit. That is already difficult to conceptualize. But the corona, the wispy outer halo that extends millions of miles above that surface, is over 1,000,000 degrees. That number is not a typo. The outer atmosphere is 100 times hotter than the surface it sits above. This makes no intuitive sense. If you move a thermometer away from a campfire, it gets cooler, not hotter. The normal rules of heat transfer suggest that the corona should be cooler than the surface below it. It is not. And despite decades of study and several dedicated spacecraft missions, scientists have not reached a definitive consensus on what heats the corona to such extreme temperatures. It is one of the biggest open questions in solar science. During a total solar eclipse, whether from Earth or from a spacecraft near the moon, the corona becomes visible to the naked eye. It appears as a faint structured glow extending outward from the moon's edge. It is not uniform. It has shapes, extensions, filaments, and some of those shapes carry their own names because they reveal specific physical processes happening inside the corona itself. Streamers are one of the most common visible features. They are long, bright extensions of solar material, stretching outward from the equatorial regions of the star. They are caused by magnetic field lines that trap hot plasma, holding it in elongated structures that extend far into space. During the Artemis 2 eclipse, the crew saw streamers clearly. Victor Glover described them with a comparison that stuck. He said that if you have ever seen the spotlight that shines from the top of the Luxor Casino in Las Vegas at night, the streamers look like what that spotlight wants to be when it grows up: narrow, bright, extending into the darkness, shooting outward from behind the moon's edge like concentrated beams of light trapped by magnetic fields, 1,000,000 degrees hot. That description, delivered from 4,000 miles above the lunar surface, was the most vivid real-time description of coronal structure ever given by a human being from space. Scientists, back in Houston, were listening closely, and the crew was not done looking. The streamers were the obvious feature, but Glover's description of them also pointed towards something subtler that the crew detected at the edges of the main structures. They described them as baby hairs. That phrase does not appear in any astrophysics textbook, but it captured something real. Around the larger, brighter streamer structures, the corona displays finer, thinner filaments of solar material, narrow extensions of magnetized plasma that branch off from the main streamer belts and extend in slightly different directions. These secondary structures are far dimmer than the main streamers and require the right viewing conditions to see clearly. The near-total darkness of the eclipse, combined with the crew's proximity to the moon and their unobstructed view in space, made those finer features visible in a way that is extremely rare from Earth-based eclipse observations. Think of it this way: the corona is not smooth. If you could see it fully, it would look more like a firework frozen at the moment of explosion, with long bright streamers shooting outward and finer structures threading between them. From Earth, even during a perfect total eclipse lasting several minutes, atmospheric turbulence and the brevity of totality make it difficult to detect those secondary structures. From integrity, the eclipse lasted nearly an hour in the vacuum of space, with no atmospheric distortion whatsoever. The crew had the single best view of the corona ever experienced by human eyes, and they had time to actually study it. Scientists confirmed that the observations during the eclipse will contribute to ongoing research into the corona's structure and its mysterious heat. The crew's descriptions and photographs give researchers data from a vantage point and duration that no ground-based or near-Earth telescope can replicate. The corona observations from this mission are already being reviewed by solar physicists. But while all of that was happening, during that same hour of eclipse darkness, the crew was watching the surface of the moon below them. And the surface was doing something unexpected. Something was hitting it, again and again. Each strike a flash of light visible from space. Each one a rock arriving from the same dark void the crew had just passed through on the far side. The universe, it turned out, was putting on more than one show at once. 6 flashes, 6 rocks arriving at full speed. During the eclipse, as the moon's surface sat in darkness below them, the crew watched light appear where there should have been none. Each flash lasted a fraction of a second. Each one was a meteoroid, arriving from the dark, striking the surface with enough force to release visible energy from 4,000 miles away. The crew reported 6 of them. Scientists on the ground were already excited before the eclipse ended. They reminded the crew that citizen astronomers on Earth who monitor the moon for exactly these kinds of events might have caught the same strikes with backyard telescopes, since the impacts occurred on the near side, near and south of the equator. Cross-referencing those observations with amateur recordings from Earth could produce a matched dataset of real scientific value. But the deeper significance of those 6 flashes goes far beyond the mission. The moon sits in the same stream of debris we do. Every rock that crosses the moon's orbit also crosses Earth's orbit. Our planet is larger. Our gravity is stronger. We attract more of them. The difference is our atmosphere. A rock that hits the moon arrives at full speed and punches directly into the surface. A rock that enters Earth's atmosphere at the same size burns up as it descends. What you call a shooting star is usually a pebble or a grain of gravel, heated to glowing by the friction of our atmosphere and consumed before it reaches the ground. The moon has no atmosphere. Every single object, from a dust grain to a house-sized boulder, hits the surface and stays there. This means the moon acts as a partial shield. Its gravity catches some objects that might otherwise have continued on toward Earth. Its surface absorbs impacts that our atmosphere, at certain sizes and angles, would not have been able to stop anyway. Scientists use the moon's impact rate to model how many objects are crossing our orbital neighborhood right now. The 6 flashes the crew saw were not exceptional. Thousands of such impacts occur across the lunar surface every year. The difference is that most go unobserved. These 6 happened while 4 human beings were watching, with darkness helping them see. Each flash was a reminder. The solar system is still active. The debris field that hammered every rocky world in the early solar system is not gone. It is still out there, thinned out by billions of years of collision and clearing, but present. And the far side of the moon carries the fullest record of every time that debris field scored a direct hit. The moon's lack of atmosphere is not just what makes impact flashes visible. It is what makes the far side one of the most scientifically valuable surfaces in the inner solar system. On Earth, the geological record is constantly being erased. Plate tectonics push crustal sections under each other, recycling rock back into the mantle. Rain and wind carve away surfaces. Volcanic activity buries old terrain under new lava. The oldest exposed rock on Earth's surface goes back roughly 4 billion years, and even that is exceptionally rare, found in tiny outcrops in Canada and Australia. The vast majority of Earth's surface is geologically young, constantly renewed. The far side of the moon is the opposite. Nothing erases it. There is no rain, no wind, no plate tectonics, no active volcanism in the areas the crew observed. The only force reshaping the surface is impacts. And impacts do not erase the record. They add to it. Each new crater sits on top of the older ones, layering the timeline deeper rather than wiping it clean. The oldest surfaces on the far side are estimated to be 4 billion years old or more. They formed during the period scientists call the Late Heavy Bombardment, a phase in early solar system history when the debris field was so dense that worlds across the inner solar system were being struck relentlessly. Earth experienced the same bombardment, but every trace of it has been erased by 4 billion years of active geology. The moon kept the record. Every crater the Artemis 2 crew photographed from their window was a data point about an event that happened somewhere between 100 million and 4 billion years ago. The density of craters in a given area tells scientists how old that surface is. The sizes of craters tell scientists what size of objects were flying through the inner solar system at that time. The chemical composition of material exposed by impacts tells scientists what the moon was made of at different depths. This is the archive that no other object in the inner solar system has preserved, and the far side has more of it than anywhere else. The thick crust kept the surface intact through events that would have flooded the near side's record with lava. Every ancient impact stayed exactly where it landed. The crew documented what they could in 7 hours. Scientists will be analyzing those images and descriptions for years. But the archive holds one entry so large that it changes the scale of everything around it. The South Pole Aitken Basin is not just the largest crater on the moon, it is the largest confirmed impact structure in the entire solar system. And it sits on the far side, mostly hidden from Earth, one of the most significant geological features our species has ever had the ability to study. Picture this. The basin stretches from the moon's south pole all the way to a smaller crater called Aitken, near the equator. The distance across it is roughly 1,500 miles. For context, the continental United States from coast to coast is about 2,800 miles wide. The South Pole Aitken Basin would cover more than half that distance. It is roughly circular, and at its center, it reaches a depth of around 8 miles below the surrounding terrain. It formed approximately 4 billion years ago when an enormous asteroid struck the far side. The impact was so violent that it excavated material from far below the moon's crust, pulling up rock from regions that would normally be completely inaccessible. That excavated material holds the potential to tell scientists things about the moon's interior that no other location on the surface can provide. And in 2019, scientists discovered something buried underneath it that no one had expected. Using data from the Gravity Recovery and Interior Laboratory mission, which precisely measured tiny variations in the moon's gravitational pull, a team led by researchers at Baylor University found a mass deep beneath the basin that should not be there. Something dense, something heavy, something pulling the crater floor downward by more than half a mile, sitting roughly 200 miles below the surface. The leading theory is that it is the metallic remnant of the asteroid that caused the impact. Under the right conditions, computer simulations suggest that the iron and nickel core of a large asteroid might not fully escape the impact site. Instead, it could be dispersed into the upper mantle and remain there, suspended by the surrounding rock, for billions of years. Scientists calculated that the dispersed core of the asteroid that formed the South Pole Aitken Basin could match the mass of the anomaly detected, a buried asteroid. Still there, 4 billion years later, the Artemis 2 crew flew over the edge of this basin. The images they captured of its terrain will contribute to the planning of future surface missions aimed directly at unlocking what lies inside it. One of the confirmed findings from the Artemis 2 flyby surprised even the scientists who had predicted it. During their observation window, the crew documented ancient lava flows on the far side. These are regions where volcanic rocks seeped out and spread across the surface, cooling into the dark, flat material that looks so different from the pale highland terrain around it. On the near side, this volcanic material covers roughly 31% of the surface. On the far side, scientists expected almost none because the thick crust should have been too dense for magma to break through. Some lava flows exist. They are smaller, less extensive, and found in specific regions where the crust may be locally thinner, perhaps near impact basins where ancient collisions removed material from above the mantle. The crew photographed these flows and described their color and texture variations to scientists in Houston. Even a thin coating of volcanic rock on a far side surface tells researchers that heat was somehow delivered to that region. Something drove the magma upward. The question of what generated that heat connects back to the moon's interior, which continues to be more active than textbooks from 30 years ago suggested. The moon is still cooling, its interior is still contracting, and that contraction is not gentle. Thousands of thrust faults have been mapped across the lunar surface by the Lunar Reconnaissance Orbiter over the past 15 years. These are places where the crust has buckled as the moon shrinks, one section of rock being pushed up and over another as the interior slowly cools. The fault scarps, small cliff-like steps in the terrain, look young. Their surfaces have not been ground down by micrometeorite impacts in the way that older features have. Many of them appear to have formed within the last 50 million years, which is geologically recent. Scientists analyzing data from the Apollo seismometers, left on the surface between 1969 and 1977, found that some of the shallow moonquakes recorded during those years occurred near these faults. The moon was shaking itself along active fault lines while the Apollo instruments were listening. It is still doing it today. And Artemis 4 will land near the South Pole, directly in a region where some of the strongest recorded moonquakes have been traced. The moon shrank by roughly 100 meters in diameter over the last few 100 million years. That number sounds small, but for a world with no plate tectonics, no ocean, and no atmosphere, any geological activity is significant. The moon's contraction is driven entirely by the slow loss of internal heat. As the interior cools, it contracts, and the rigid outer shell is forced to compress. Something has to give. The crust buckles, and faults form. Researchers published findings in early 2026, identifying over 1,000 new fault ridges in the lunar Maria, the dark volcanic plains visible on the near side. These are subtle structures, small compressional ridges that form through the same mechanism as the larger fault scarps. Each one represents a place where the crust is under stress, and because they share the same formation mechanism as the larger scarps already linked to recorded moonquakes, each one is a potential source of future seismic activity. The significance of this for Artemis is concrete. Astronauts are going to live and work on the lunar surface. Equipment will be placed on the ground. Habitats will be constructed. If the ground can shake, engineers need to know where the shaking is most likely to happen. The crew of Artemis 2 documented surface fractures and faults during their flyby. From 4,000 miles up, they could observe longer structures and wider geological patterns than any robotic orbiter has been able to describe with human judgment applied in real time. Their observations will feed directly into the site selection process for Artemis 4's landing near the South Pole. The South Pole is also where ice has been confirmed in permanently shadowed craters. Craters so deep that the star whose light reaches the moon's surface never illuminates their floors. In those permanently frozen shadows, ice from ancient comets, asteroids, and possibly even volcanic outgassing has accumulated over billions of years. That ice is not just a resource for future astronauts to convert into water and rocket fuel. It is a 4 billion-year archive of everything that struck the moon. And that archive is the reason scientists describe the South Pole as possibly the most scientifically valuable piece of real estate in the entire solar system. During the eclipse, while the moon blocked the star's light and the corona glowed around the lunar edge, something else appeared on the surface below the crew: Earthshine. Victor Glover called down to mission control seconds after the star disappeared behind the moon. He described seeing it immediately. Earthshine is the faint illumination of the moon's night, side by light reflected from Earth. When you look at a crescent moon from Earth and can faintly see the dark portion of the disk, that ghostly visibility is Earthshine. Earth's day side is reflecting light onto the lunar surface, dimly illuminating the shadowed part of the moon. From where the Orion crew sat, they were looking at the moon from the other direction. The dark portion of the moon was below them, and it was faintly lit by light bouncing off Earth. The planet was not visible from behind the moon at that moment, but its light was. Earth's reflection reached around the edge of the moon and landed softly on the surface, thousands of miles below the crew. Scientists hope to study Earthshine during the eclipse because it can reveal information about Earth's own reflectivity. The intensity of Earthshine depends on how much of Earth's surface is covered by bright features like clouds, ice, or ocean. Measuring it from the moon's vicinity gives researchers a new vantage point for studying Earth's energy balance, the amount of light our planet reflects versus the amount it absorbs. That balance is directly connected to climate. The crew looking at the moon's dark surface, gently lit by their own planet, was one of the quieter moments of the mission. 4 people behind the moon, cut off from every signal Earth produces, watching their home's reflection fall softly onto the surface of another world. It was, in the most literal sense, seeing Earth from the outside. And while they watched Earthshine, something else caught the attention of the scientists in Houston, who were waiting for it. The zodiacal light appeared in one of the crew's early photographs. It is an odd, faint phenomenon, a subtle glow in the sky that most people on Earth have never seen, because it requires very dark skies free of light pollution to be visible at all. From space, away from Earth's atmosphere, it is clearer. During the eclipse, with the star's light blocked and the sky around the moon falling into deep darkness, the conditions were ideal. Zodiacal light is the visible trace of a vast cloud of dust spread across the inner solar system. The dust is microscopic, grains no larger than smoke particles, but there is so much of it that when starlight shines on it and scatters toward an observer, the collective glow is visible. The dust is concentrated along the plane of the solar system, the flat region where all the planets orbit. From Earth, the zodiacal light appears as a faint pyramid of glow above the horizon after sunset, or before sunrise, tracing the path of the planets across the sky. From the crew's position near the moon, the glow traced the entire ecliptic plane. They were looking at the skeleton of the solar system, lit up by scattered starlight. The origin of that dust is still debated. For decades, scientists assumed it came from asteroid collisions and comet tails. But data from the Juno spacecraft, which traveled through the inner solar system on its way to Jupiter, suggested something surprising. The dust distribution appears to match the orbital path of Mars. Some researchers now believe that fierce dust storms on Mars may be the primary source of the interplanetary dust that produces the zodiacal light. If that is correct, the faint glow the Artemis 2 crew photographed during the eclipse is partly a reflection of Martian weather. Dust lofted from the surface of Mars by planet-scale storms, escaping into orbit, spreading across the solar system, and eventually becoming the glowing background against which planets and stars are observed. The crew photographed it. Scientists will analyze the images carefully, but while the zodiacal light was the subtlest thing the crew saw during the eclipse, the most visually overwhelming moment came from something much simpler. The sky around the darkened moon, stripped of the star's glare, suddenly full of planets. During the eclipse, as the star's light disappeared behind the moon, the darkness around it deepened, and then the planets appeared. Saturn, Mars, Venus, Mercury, all of them visible simultaneously, arrayed in the darkness around the eclipsed star. From Earth, seeing multiple planets at once requires specific alignments and favorable conditions. From the crew's position in space, with no atmosphere to scatter light, and the star's glare blocked entirely, the planets of our solar system emerged in the darkness as distinct bright points in a way that no human had experienced from that specific vantage point in history. Mission science-led Kelsey Young confirmed that the crew had line of sight to all 4 of these planets during the eclipse, along with a range of star constellations. The crew turned their cameras to capture as much as they could during the brief window of eclipse darkness. What they were seeing was the ecliptic plane, the same flat disk of space where the planets orbit, the same plane lit from edge to edge by the zodiacal dust. All of those worlds orbit in roughly the same flat ring around our star, because they all formed from the same flat spinning disk of gas and dust 4.5 billion years ago. The disk collapsed into a plane. The planets formed within that plane, and they have been orbiting in it ever since. From behind the moon, with the star blocked, the crew had a view of that architecture that no photograph from Earth can replicate. The scale of the solar system laid out in one sweep of the eye. Astronomer and science communicator Noah Petro described the moon as the 8th continent of Earth. When you study the moon, he said, you are really studying an extension of Earth. The same origin, the same history of bombardment, the same solar system. The moon just kept the records that Earth lost. And standing at the far end of those records, staring back at a solar system that was briefly laid bare by darkness, the Artemis 2 crew caught a glimpse of what it feels like to see everything at once. But there was someone who had been there before, and before the crew wrapped their historic flyby, they heard his voice. Before the flyby began, the crew heard a recording. Jim Lovell was 97 years old when he died in 2025. He had flown on Apollo 8, the first crewed spacecraft to orbit the moon, and on Apollo 13, the mission that nearly cost him and his crew their lives. He had seen the far side of the moon with his own eyes. He had been among the first humans to witness Earthrise. His photograph of Earth rising above the lunar horizon from Apollo 8 became one of the defining images of the 20th century. Before he died, he recorded a message for the Artemis 2 crew, and on the morning of the flyby, day 6 of the mission, Mission Control played it for them as they approached the moon. The message was brief. He told them to welcome to his old neighborhood. That phrase, arriving at that moment, carried the weight of 58 years of human absence from the moon's vicinity. Lovell had seen the far side from Apollo 8 in December of 1968. The Artemis 2 crew was seeing it again, for the first time since in April of 2026. Between those two dates, no human had gone back. An entire generation had lived and died without any of our species venturing even close to another world. Mission Commander Wiseman said there was a little bit of giddiness on the crew when they heard it. Kelsey Young, the lunar science lead, called it amazing news. And then the crew went to work. What Lovell could not have known when he recorded that message was that the crew who received it would go farther from Earth than he ever had. Apollo 13, his most harrowing mission, set the record for farthest human spaceflight from Earth. In 1970, driven off course by an oxygen tank explosion that nearly killed the crew. The Artemis 2 crew, deliberately and safely, surpassed that distance by over 4,000 miles. And when they broke that record, the moon outside the window was not the moon Lovell had seen. It was the stranger one. Before any human could see the moon's far side properly, a pair of small spacecraft flew it in circles and mapped what was invisible. The Gravity Recovery and Interior Laboratory mission launched in 2011 and placed two small spacecraft in precise lunar orbit. Their job was not to photograph the surface, it was to measure gravity. The two spacecraft flew in formation, trailing each other in orbit. As the leading spacecraft passed over a dense region of the moon, its orbit was subtly pulled forward by the extra gravitational tug. That tiny change in the distance between the two spacecraft was measured continuously by radio signals bounced between them. The precision was extraordinary. Scientists could detect changes in the gap between the two craft equivalent to a fraction of the width of a human hair. By mapping those gravitational variations across the entire surface, including the far side, the mission produced the most detailed map of the moon's interior structure ever created. It revealed the thickness of the crust everywhere. It confirmed that the far side crust is significantly thicker than the near side crust. It revealed the buried mass anomaly under the South Pole Aitken Basin. It showed the locations of ancient buried impact basins that are invisible on the surface but detectable through their gravitational signatures. The Grail data transformed how scientists understand the moon. It turned the interior from a guessed-at mystery into a mapped structure, at least in broad terms. And it provided the framework against which all subsequent missions, including the visual observations made by the Artemis 2 crew, can be interpreted. When Wiseman called out a geological feature, the scientists in Houston already had the gravity map telling them what the crust underneath it should look like. When Koch described a difference in surface brightness, the geochemical maps could help explain what minerals were causing it. The crew's eyes and the orbiting data, together, were a combination that neither could produce alone. But there are still things Grail could not tell us. The gravity maps reveal mass. They do not reveal chemistry, mineralogy, or the detailed history of any specific layer of rock. Those answers require boots on the ground and samples brought home. Scientists agree on what makes the moon strange. They do not fully agree on why. The two-faced moon, with its thin-crusted volcanic near side and its thick-crusted cratered far side, has produced three serious competing explanations. Each one is supported by different lines of evidence. Each one explains some features well and struggles with others, and none of them has yet been definitively proven. The first theory is the Earthshine hypothesis. When the moon was still a glowing ball of molten rock, its near side faced a hot young Earth radiating enormous amounts of heat. That heat kept the near side warmer longer, slowing the crystallization of light minerals there and allowing them to drift toward the cooler far side. The far side, facing open space, cooled faster, built up more light crust minerals, and ended up thicker. This is mathematically plausible, currently regarded as a leading explanation, and awaiting confirmation through simulation. The second theory involves the South Pole Aitken Basin impact. The enormous asteroid that struck the far side roughly 4 billion years ago would have sent a massive heat plume through the lunar interior, toward the near side. That plume carried heat-producing elements to the near side, making it internally hotter, more volcanically active, and thinner. This theory is supported by geochemical maps, showing those heat-producing elements concentrated on the near side. Scientists at Brown University published strong evidence for this mechanism in 2200. The third theory is the twin moon hypothesis. A second, smaller companion moon formed alongside our moon from the same debris cloud and spent tens of millions of years in a shared orbit, before slowly colliding with the far side. Its material piled onto the far side crust, thickening it. The highlands of the far side are the remnant of that merger. This theory is supported by the distinct composition and elevation of the far side highlands, but requires a specific set of orbital conditions that are difficult to verify. All three theories may carry partial truth. The moon's asymmetry could be the result of multiple overlapping processes. Or one of them is correct, and the others are red herrings. Artemis 4, targeting the South Pole in 2028, will land directly adjacent to the South Pole Aitken Basin. The samples it brings back will be the first from that region in human history, and those samples may finally break the tie. The observations from Artemis 2 do not just answer questions, they sharpen the ones scientists already had. The geologic observations made during the flyby will directly inform the planning for Artemis 4, currently scheduled for 2028. That mission aims to land 2 astronauts on the lunar surface near the South Pole, in a region of extreme terrain, permanent shadow, and ancient crater floors where ice has been confirmed to exist. The ice matters for 2 reasons. The practical one first. Ice at the lunar South Pole can be processed into water for astronauts to drink, oxygen for them to breathe, and hydrogen and oxygen for rocket fuel. A sustained human presence at the moon becomes dramatically more viable if the raw materials for sustaining it are already there. But the scientific reason is equally powerful. The ice in those permanently shadowed craters is ancient. It accumulated over billions of years from the impacts of comets and water-bearing asteroids, and it has been frozen there, untouched, undisturbed, in permanent darkness since it arrived. It is a sample library of everything that struck the moon over 4 billion years, preserved as ice. When scientists analyze that ice, they will find traces of the comets and asteroids that delivered it. The chemical signatures of those objects will tell researchers what kinds of bodies were crossing the inner solar system at different points in history. And because those same kinds of objects were striking early Earth at the same time, the Lunar Ice Archive is partly an archive of what seeded early Earth with water, organic molecules, and potentially the precursor ingredients of life. The moon kept the record. The South Pole kept the oldest parts of it frozen. Artemis 2 showed scientists where to look from orbit. Artemis 4 will put people on the surface to start reading what is actually written there. And the question that sits underneath all of it, the one scientists describe as the most fundamental, is one that the moon's far side makes impossible to ignore. While the crew was behind the moon, Mission Control sat in silence. For 40 minutes, the screens that track spacecraft telemetry went still. The data feeds from Integrity stopped updating. Flight controllers who had spent years training for this moment could do nothing but wait. Their jobs, which normally involve monitoring dozens of systems simultaneously and responding to any anomaly within seconds, were reduced to watching a clock. Lead Flight Director Jeff Radigan later described anticipating what he called an irrational fear that is part of human nature during the blackout, specifically during the final moments before the crew re-emerged. The closest human equivalent is the way any person feels during those minutes before an important outcome is confirmed. The last moments before the call comes through, before the results appear, before the unknown becomes known. The crew, by contrast, was busy. During the 40 minutes of silence, they were moving through their observation checklists. They were photographing the surface. They were calling out features to each other. They were doing the work they had trained years to do, cut off from every other human being on Earth, with a surface below them that no human had ever observed from that position before. Victor Glover, asked afterward what it felt like to be completely isolated from humanity, gave an answer that surprised some people. He said it was actually quite nice. The silence created focus. The absence of radio chatter cleared space for concentration. The crew turned inward and worked. When signal returned and Houston heard their voices again, there was a collective exhale from the control room. Not because anything had gone wrong, but because the 40 minutes of not knowing had ended, and 4 people had come back around from the far side of the moon, which is exactly what they were supposed to do. And then the science lead came on the line and told them what they had accomplished. She said they had brought the moon closer for every scientist and every person watching. She said they could not say thank you enough. When Integrity reached its maximum distance from Earth, 4 people had traveled farther from home than any human being in history. The previous record was held by the crew of Apollo 13, set in April of 1970, during one of the most harrowing spaceflight emergencies ever experienced. An oxygen tank in the service module exploded 2 days into the mission, crippling the command module and forcing the crew to use the lunar module as a lifeboat. To get home safely, they swung around the far side of the moon on a trajectory that took them farther from Earth than any crewed mission ever had. Their maximum distance from Earth was approximately 248,000 miles. They did not set that record on purpose. They set it because the explosion had left them no choice. The Artemis II crew surpassed it by over 4,000 miles, deliberately, safely, on a trajectory designed years in advance. At maximum distance, Earth was no longer a planet in any experiential sense. It was, as Commander Wiseman described it, a small crescent, something you could block from view by holding up a finger. The moon beside them was enormous, roughly 3 to 4 times the angular size of Earth from that position. And it was almost full. What humans call the moon from Earth, the familiar disk in the night sky, was from that position, a vast world filling a significant fraction of the view. The crew had not just broken a record, they had stepped across a boundary that only 12 humans in history had crossed before them, the boundary between Earth's near vicinity and the actual vicinity of another world. Apollo astronauts, between 1968 and 1972, were the only others. Now, 54 years later, 4 more people joined that small category of human beings who have been genuinely far from Earth. And unlike the Apollo crew that set the previous record, they came home on schedule. At 5 minutes past 5 in the afternoon on April 10, 2006, the Orion capsule hit the Pacific Ocean off the coast of California. The heat shield had done its job. The parachutes had deployed correctly. The USS John P. Murtha was waiting nearby. The recovery ship positioned based on forecasts of wave height, wind speed, and cloud coverage that mission planners had been monitoring for days. The splashdown was smooth. 4 people climbed out of a spacecraft that had carried them around the moon and back. They were the first humans to return from lunar distance since Eugene Cernan and Harrison Schmitt stepped off the moon's surface in December 1972. Everything since then had been within Earth's near vicinity. For over half a century, our species had not sent anyone truly far away. Now they had been. What the crew carried back cannot be weighed on a scale. There are no lunar samples from this mission, no physical material scooped from the far side's ancient terrain. What they brought back is different. Direct human observation of a landscape that had never been seen with human eyes, delivered with geological training, real-time judgment, and the pattern recognition that comes from a person physically present in a place, rather than receiving data from a robot. The images they sent back will be analyzed for years. The verbal descriptions they made during the flyby have already helped refine the list of scientific targets for Artemis 4. The 2 provisional crater names they proposed, Integrity and Carroll, await formal submission to the International Astronomical Union. The mission data from Integrity, every sensor reading, every telemetry point, every flight parameter recorded across 10 days in deep space, will inform the engineering design of every future crewed mission that attempts anything more ambitious. Artemis II was the shakedown run. The spacecraft worked, the crew worked, the plan worked. And what the crew saw on the far side is already changing how scientists think about what they will send future missions there to find. The far side of the moon is not a mystery solved. It is a mystery made specific. Before April 6, 2026, The questions scientists had about the far side were broad. Why is it different? What processes shaped it? What does the ancient record of its surface tell us about the inner solar system 4 billion years ago? After April 6th, those questions have sharper edges. The crew's observations of lava flows where the crust should have been too thick for them. The surface fractures from a moon still contracting. The 6 impact flashes from a debris field, still active. The images of ancient basin walls, crater floors, highland textures. These are not answers, they are better questions. There is a buried mass the size of 5 Hawaiian islands, sitting below the largest crater in the solar system. On the far side, 200 miles underground, scientists believe it is a metallic asteroid, lodged there 4 billion years ago, and never extracted by the forces that would have moved it on an active world. If Artemis 4 reaches the South Pole and brings back samples from the edge of that basin, laboratory analysis might confirm the composition of the buried mass without ever drilling down to it. There are 3 competing theories for why the far side has a thicker crust than the near side. All 3 are scientifically credible. All 3 predict slightly different chemical compositions in the rock at the South Pole. Samples from that region could in principle tell scientists which one is right, and in doing so, reveal something fundamental about how the moon formed and how early Earth shaped its nearest neighbor. There is 4-billion-year-old ice in permanently shadowed craters at the South Pole, ice that carries a molecular record of everything that struck the moon across the entire history of the solar system. And some of those molecules, scientists believe, are the same ones that arrived on early Earth and helped set the stage for the chemistry that eventually produced life. The far side of the moon has been hiding half its face since before humans existed. 4 people just looked directly at it for 7 hours. What they saw was not an answer. It was a door. And in 2028, if all goes as planned, other people will walk through it. Before the moon existed, Earth had no moon, and early Earth was a very different place. 4.5 billion years ago, the inner solar system was crowded. The planets had not yet settled into their current orbital lanes. Protoplanets, rocky objects the size of Mars or larger, were still moving through the region in unstable paths. And one of them, a world scientists now call Theia, was on a collision course with the young Earth. Theia did not survive. In the most violent event in Earth's history, the 2 worlds collided. The impact released more energy than is possible to describe in any everyday comparison. Both bodies were partially vaporized. Material from Theia and from Earth's outer layers was thrown into orbit around the surviving we-shaped Earth. And from that orbiting cloud of rock and vapor, over thousands of years, the moon coalesced. This is the giant impact hypothesis, and it is the leading scientific explanation for the moon's formation. Evidence for it runs through the chemistry of lunar rocks. The moon and Earth share isotopic signatures that are almost identical, meaning the ratio of certain atomic variants in lunar rock matches the ratio in Earth rock with a precision that rules out the moon forming somewhere else and being captured by Earth's gravity later. They were born from the same collision. A study published in late 2025 traced the composition of Theia through iron isotope measurements in lunar samples and concluded that Theia likely originated from the inner solar system, probably slightly closer to our star than Earth itself. Theia was not some distant visitor. It was a neighbor, a world that formed in the same neighborhood as Earth, grew to roughly the size of Mars, and eventually fell inward onto a collision path from which there was no recovery. The far side of the moon carries the oldest surfaces from the aftermath of that collision. 4.5 billion years of history, compressed into ancient highland crust that formed in the first few 100 million years after the moon's birth. When the Artemis 2 crew looked down at those highlands and described their texture and color, they were describing the closest thing that exists to the original material of our earliest neighbor. Before the moon tidally locked itself to Earth, it was spinning faster, much faster. When the moon first formed from the debris of the Theia collision, it was much closer to Earth than it is now. Some estimates suggest it was as close as 1/10 of its current distance. At that proximity, the gravitational interaction between the 2 worlds was intense. Earth's gravity pulled differently on the moon's near side than its far side, and that unequal pull acted as a brake on the moon's rotation. Slowly, across millions of years, the moon's spin rate decreased, until it reached the point where one rotation took exactly as long as one orbit around Earth. At that moment, one face locked permanently toward Earth, the other locked permanently away. The same process was happening to Earth, just much more slowly. The moon's gravity pulls on Earth's oceans and crust with a slightly unequal force too, and that force has been acting as a brake on Earth's rotation for 4.5 billion years. When Earth first formed, a day was roughly 6 hours long. The moon's tidal drag has been lengthening Earth's day ever since, at a rate of about 2.3 milliseconds per century. That is tiny, but across billions of years, it adds up to 18 hours of additional day length. Today, a day is 24 hours. Without the moon and its tidal braking, Earth would still be spinning close to its original rate. A 6-hour day would mean faster winds, stronger storms, a more turbulent atmosphere, and a climate that behaves very differently from the one that supported the development of complex life. The moon did not just shape the tides. By slowing Earth's rotation, it helped shape the conditions under which life evolved. The far side of the moon, the side the Artemis II crew saw for the first time with human eyes, locked into its permanent orientation toward deep space in those early, violent years. It has faced away from Earth ever since the moon was young, while the near side experienced billions of years of Earthshine, reflected light, and the full gravitational dialogue with our planet. The far side has faced outward, silently accumulating craters, witnessing the slow clearing of the debris field, recording events that Earth cannot. The far side of the moon is the quietest place in the known solar system. Not quiet in the everyday sense. Sound does not travel in a vacuum, so the moon's surface is silent regardless of which side you are on. The quiet the far side possesses is electromagnetic. Every radio signal generated by human civilization, every broadcast tower, every satellite communication, every Wi-Fi router and mobile phone and radar installation on Earth generates radio waves that spread outward in all directions. The near side of the moon sits in that radio environment, exposed to the full electromagnetic noise of a technological civilization. The far side has the moon's solid body between it and all of that. 2,000 miles of rock, thousands of miles thick at the equator, blocking every human-generated radio frequency from reaching the surface. From the far side, Earth is electromagnetically silent. Scientists have recognized for decades that this makes the far side the ideal location for radio telescopes capable of detecting signals that are simply impossible to study from Earth. Earth's atmosphere reflects and absorbs certain very long wavelength radio frequencies before they reach the ground. Ground-based telescopes cannot detect them at all. Telescopes on the near side of the moon would see Earth's radio noise drowning out the faint cosmic signals they are trying to detect. But a telescope on the far side, shielded by the moon itself, could detect radio frequencies that have never been studied by any instrument built by humans. Those frequencies carry signals from the universe's earliest era. Before the first stars formed, before the first galaxies lit up, in the period scientists call the cosmic dark ages, hydrogen gas throughout the universe emitted radio waves at specific frequencies. Those signals are still arriving, stretched by the expansion of the universe into the very long wavelengths that can only be detected from the far side of the moon. China has already proposed placing a large radio telescope array on the far side. NASA has investigated similar concepts. Scientists are actively concerned that increasing activity on and around the moon, including relay satellites, needed to communicate with far-side missions, may contaminate the radio-quiet environment before a telescope can be built there. The Artemis II crew spent 40 minutes in the far side's electromagnetic silence. No signal from Earth could reach them, and scientists want to protect that silence permanently. The Artemis II crew were not the first to see the far side up close, but they were the first humans to do so. China's Chang'e 4 spacecraft made history on January 3, 2019, when it became the first human-made object to successfully land on the far side of the moon. No soft landing had ever been achieved there before, for a simple reason: the moon's body blocks all direct radio communication between a lander and Earth. To operate a mission on the far side, China first launched a relay satellite called Queqiao, meaning Magpie Bridge, into an orbit that kept it in view of both the far side landing site and Earth simultaneously. Only with that relay in place was a controlled landing possible. Chang'e 4 touched down in the von Karman crater, a flat-floored basin sitting inside the South Pole Aitken Basin. It deployed a small rover named U-22, which has driven slowly across the far side surface ever since, becoming the longest operating lunar rover in history. What Chang'e 4 found on the surface added to the mystery. The geological composition of the von Karman crater floor showed materials that may include rock from the moon's mantle, pulled up by the ancient South Pole Aitken impact. If confirmed, that would mean a robotic rover has been driving over some of the deepest material ever accessible on the lunar surface, material that formed tens of miles below the moon's crust during the planet's earliest, most active period. Chang'e 6 followed in 2024, landing in the Apollo Basin on the far side and returning the first samples ever retrieved from that hemisphere of the moon. Those samples are still being analyzed by scientists around the world. The Artemis 2 crew flew over the region where these Chinese missions landed. They could not see the spacecraft at their altitude, but they observed the same terrain, the same ancient basin floor, from above and with their own eyes. The giant impact that formed the moon is the accepted explanation, and it is also, in one specific way, deeply puzzling. If Theia collided with early Earth and the moon formed primarily from debris ejected by the impact, most of that debris should have come from Theia rather than from Earth. Simulations of the impact suggest that the moon should be made primarily of Theia material, with a smaller contribution from Earth's outer layers. The problem is that the moon does not look like Theia material. It looks like Earth material. When scientists measure the ratios of oxygen, titanium, chromium, and other isotopes in lunar rocks, they match Earth's composition extraordinarily closely. If the moon formed mostly from Theia, and if Theia formed in a different part of the solar system with a different composition, those ratios should be different. They are not. Scientists call this the isotope crisis of the giant impact hypothesis. It is not a small discrepancy. The similarity between Earth and Moon is so precise that multiple independent isotope systems all tell the same story. These two worlds are chemically almost indistinguishable. Three main explanations exist. The first is that Theia formed in the inner solar system, very close to Earth's orbit, and therefore had essentially the same composition as Earth. The November 2025 study tracing Theia's iron isotopes supports this scenario. The second is that the impact was so energetic that both Theia and Earth were vaporized and thoroughly mixed before the moon condensed from the resulting cloud of vapor. The third is that after the collision, material from Earth and the moon exchanged enough to equilibrate their compositions. None of these explanations is fully proven. The moon formed from a catastrophic event that happened 4.5 billion years ago, and the details of that event are encoded in rock chemistry that scientists are still working to fully decode. The far side highlands, the oldest preserved surfaces from that formation period, hold some of those clues, and they are waiting for future missions to read them. The far side was hidden from humanity for the entirety of our existence as a species, and the reason it was hidden is also the reason it is scientifically extraordinary. Tidal locking happens because no world is perfectly spherical. The moon has slight variations in its mass distribution, and Earth's gravity pulls on those variations unequally. The gravitational pull on the moon's slightly denser near side is fractionally stronger than the pull on the far side. Over millions of years, that unequal pull transferred energy out of the moon's rotation. The moon slowed. Its spin matched its orbit. One face locked toward Earth and has stayed there ever since. For billions of years, this meant that every piece of rock, every crater, every geological feature on the far side existed without ever being seen by any creature on Earth. Life evolved here. Civilizations rose and fell. Humans built telescopes and looked at the moon thousands of times, and the far side sat hidden, 2,000 miles away, in plain sight of the universe but invisible to the only species that had yet developed the ability to look. The Soviet Luna 3 spacecraft photographed the far side for the first time in October 1959. The images were blurry and incomplete, but they revealed enough to shock the scientific community. The far side was not what anyone expected. No vast dark seas. Just craters and more craters. The near side and far side were fundamentally different, and no one had known. The Artemis II crew saw it with their own eyes 67 years later. They were looking at a world that hid itself from humanity for the entire length of human civilization and revealed itself only when we finally built the machines to go there. Christina Koch looked out the window and felt her brain search for something familiar. It found nothing, and that failure of recognition was scientifically one of the most important moments of the entire mission. A trained geologist, looking at the moon, knowing what the far side should look like from study and from maps, still found it wrong at an instinctual level. That gap between expectation and experience is where science lives. The moon did not just break Earth's rotation gradually. Its presence from the very beginning shaped whether complex life was possible here at all. Without the moon, Earth would still be spinning at close to its original rate. A day would be roughly 6 hours. That changes almost everything about how the planet works. A faster spin means faster winds. Earth's weather systems are driven partly by the Coriolis effect, the deflection of air and water caused by the planet's rotation. Faster rotation means stronger Coriolis deflection, which produces more extreme weather patterns. The jet streams that guide weather systems across continents would be faster and more erratic. Storm systems would be more intense. The climate would swing more dramatically between extremes. A faster spin also means stronger differential heating between day and night sides of the planet. 6 hours of sun followed by 6 hours of dark, rather than 12 hours of each, would create steeper temperature cycles. The equatorial regions would overheat during the short, intense days. The night side would cool faster. Beyond weather, the moon's tidal forces have directly shaped the evolution of life. The tidal zones where ocean meets land are among the most biologically productive environments on Earth. The rhythmic flooding and draining of tidal zones over billions of years created selective pressure for organisms that could survive periodic exposure to air. Some scientists argue that tidal zones were a critical environment for the transition of life from the ocean to land. Larger tides, driven by a closer moon in the distant past, would have created deeper and more extensive tidal zones. The rhythm of that flooding and draining may have been a driver of evolutionary development in the organisms that eventually left the water. The far side of the moon sits on the opposite end of all of this, perpetually facing away, bearing no tides, experiencing no earthshine, a world that has existed in parallel with Earth's evolution without participating in it. While the moon's near side sat above teeming oceans and developing life and rising civilizations, the far side faced the galaxy, silent and unchanged. The far side of the moon holds a scientific promise that has nothing to do with the moon itself. In the universe's very earliest period, before the first star ignited, the cosmos was filled with hydrogen gas. That gas, cooling and beginning to collapse under gravity, emitted radio waves at a specific frequency. Those waves have been traveling toward us ever since. They are still arriving. But by the time they reach Earth, the expansion of the universe has stretched their wavelength into the very long radio frequencies that Earth's ionosphere reflects back into space. No ground-based telescope has ever detected them. Scientists call this period the Cosmic Dark Ages. It lasted from roughly 300,000 years after the beginning of the universe, until the first stars lit up. About 100 to 200 million years later, everything that happened during that time, every detail of how hydrogen began to collapse into the first structures that would eventually become galaxies and stars, is recorded in those radio signals. We have never been able to read them. A radio telescope on the far side of the moon would be shielded from Earth's radio noise and free from the ionospheric barrier. For the first time, the signals from the cosmic dark ages could be detected, processed, studied. Scientists could reconstruct, frequency by frequency, what the universe looked like in those first 100 million years before a single star existed. Several concepts for such a telescope have been proposed. NASA's Lunar Crater Radio Telescope concept suggested placing a large mesh antenna inside a natural crater on the far side, using the crater walls as the rim of a dish. China has proposed a far larger array of thousands of antennas. Both concepts are technically feasible. Both face the same obstacle. Any relay satellite needed to communicate with the telescope would itself generate radio interference, potentially contaminating the signal the telescope is trying to detect. The Artemis II crew passed over craters on the far side that could one day house such an instrument. The terrain they photographed is the terrain scientists are evaluating for this purpose. And the silence the crew experienced during their 40-minute blackout, the total absence of all Earth signal, is the exact silence astronomers want to preserve and exploit. There is a question worth asking directly. Why send humans rather than robots? Robotic missions to the moon are cheaper, safer, and can last much longer on the surface than any human crew. China's U-22 rover has operated on the far side for years. Orbital spacecraft have mapped the moon's surface in extraordinary resolution. The Lunar Reconnaissance Orbiter has returned more data about the moon than any crew could collect in a lifetime of visits. What humans add is not data collection speed, it is judgment. During the Artemis 2 flyby, the crew looked at the far side terrain and made real-time assessments that no algorithm duplicates cleanly. When Koch described a color difference in a crater floor, she was applying pattern recognition developed through years of geological field training in Iceland and other Earth-based analog sites. When Wiseman suggested a provisional name for an unnamed crater, he was noting a specific feature worth remembering. When Hansen described what he saw during Earthset, he was conveying an experiential response that helps scientists understand what the human brain processes in that environment. Scientists studying the moon describe humans and robots as complementary, not competing. A geologist walking across a field notices things that a camera rolling past would not, the way a rock sounds when tapped. The subtle difference in surface texture between two adjacent areas, the intuition that something about a particular outcrop deserves a second look. Those intuitive assessments lead to sample choices, and the samples brought back from Apollo, now over 50 years old, are still being actively studied with new techniques that did not exist when they were collected. The Artemis 2 crew brought no samples home, but what they brought back in their descriptions, their photographs, and their real-time geological assessments has already refined the planning for Artemis 4 in ways that orbital data alone could not have achieved. Planetary scientist Noah Petro described the moon as the eighth continent of Earth. You do not study a continent only by satellite. After everything the Artemis 2 crew saw, after 7 hours of observation, 6 meteoroid flashes, a solar eclipse no human had witnessed from that position, a buried asteroid the size of 5 Hawaiian islands, beneath the largest crater in the solar system, ice carrying the molecular record of 4 billion years of cometary impacts, and ancient lava flows on a surface that should have been too thick to allow them. One question remains at the center of all of it. Why is there a moon at all? That sounds like a strange question to ask after 33 chapters of science. But the moon's existence is not guaranteed by any planetary formation model. Most planets do not have large moons in close orbits. Mars has 2 tiny captured asteroids. Venus has none. Mercury has none. Earth has a moon that is disproportionately large compared to our planet, large enough to have shaped our rotation, our tides, our climate, and possibly the conditions under which life developed. The isotope crisis in the giant impact hypothesis is still unresolved. Scientists agree that a large impact happened. They disagree about the details of how the resulting debris produced a moon that looks so much like Earth. The competing scenarios, Theia from the inner solar system, a high-energy complete mixing event, a post-impact chemical equilibration, all predict slightly different things about what the moon's oldest rocks should contain. The Farside Highlands are the oldest rocks. They formed in the first few 100 million years after the moon existed. Whatever process shaped the moon during those early years left its fingerprints in those ancient crusts. The samples brought back by Chang'e 6 from the Farside's Apollo basin are being analyzed. The samples that Artemis 4 will collect near the South Pole Aitken Basin may complete the picture. The crew of Integrity flew 7 hours above those rocks. They looked down with trained human eyes at a surface that held the answers scientists most want, and they came home with better questions than they left with. That is what exploration is. The crew saw something on the far side that felt wrong, that challenged instinct, that resisted the brain's attempt to match it to anything familiar. And that discomfort is not a problem to be solved. It is the engine of science. The far side of the moon is not unexplainable, but right now, it is not fully explained. And the gap between those two things is exactly where the next 40 years of lunar science will live.